Hello. Oh, holy shit. Mic check. Um, hey everyone. How's everyone doing? All good? All right. So my name is Ashim. Today I'm going to be presenting about a project I did, or I'm still doing since last spring, which is data curation for training cybersecurity focused LLMs. Um, wait, hold on. What? All right. My introduction. My name is Ashim Mahara, and I'm doing my master's in cybersecurity here. Um, I've done a bunch of things. Professional things, well, I've been working in detection engineering for some time, but my focus is on applying ML and data analytics for detection engineering. Outside of that, well, I did a Vipassana meditation course once. I've gone solo trekking, backpacking. I also do beat poetry. My favorite authors are Kerouac, Murakami, and Kafka. Um, okay, so let's start with an introduction to LLMs. So what are LLMs? Right now, most of them are primarily trained on text. When I say trained, they are pre-trained, which means that you have some data and then you train the LLM to predict the next word. Well, that's just it. But um, the data is important in this case, and what you're actually doing is you're maximizing the probability of the next word given the current word and the past context that the LLM has already seen. The backbone of most of the models that we see right now is the transformers model, um, which was popularized after attention is all you need paper. And transformers are only using the attention mechanism for doing a lot of their processing inside of them. Um, the transformers architecture, talking a little bit about history, they superseded the recurrent neural networks architecture. If somebody's into ML and DL, RNNs were used for sequential processing, but there were two main problems with RNNs, which was vanishing gradients. Because if the sequence is long, because of how the RNN has the architecture, the gradients while training would vanish because they didn't have skip connections, which we're going to see next. Um, and RNNs are very hard to train due to linear dependencies between sequence processing. So the gradients have to be, or the tokens or the probabilities have to be processed in sequence, and they have to be backpropagated in sequence. So this is the transformers architecture that powers most of the LLMs today. When I was talking about the skip connections, I was actually talking about these things, which is how the gradient sort of propagates even though it is a longer sequence, and also the multi-head attention, which looks at all the input tokens that it has processed and calculates the attention scores for the next token, or for doing the next token prediction. So there's this thing called LLM alignment, which is kind of the thing that powers a lot of, or which is part of the reason why we have GPT-4 and 4.0 and everything else, which is reinforcement learning with human feedback and other approaches. It was popularized by GPT-3. So the steps for this is actually very simple. So you collect questions or prompts, and then ask humans to produce answers for those prompts. Um, so if you have a vast amount of data that way, you will use human experts to rank those answers, and then use a very high scoring answer to train the LLM. Now the training of the LLM is primarily done in two ways, which is the supervised fine tuning on human responses, which is actually the same as the pre-training, which is next token prediction. Or you train using reinforcement learning algorithms, where the next token is actually the action provided that the previous tokens and the context are the environment's outputs. Um, Another thing that was also popularized was training a reward model. Reward models can be used to rank the responses, so you don't have to use human annotators for if you have a sufficient amount of data. This is actually taken from the OpenAI blog, which you can see is what they do. They have a data set of prompts, and they will generate responses for those prompts, use human laborers to rank those responses, train the reward model ranking the responses, and then train the GPT-3, GPT-4, GPT-5, whatever models using reinforcement learning algorithms. And the reward model determines how good the answer actually is without having human annotators do that for a lot of the queries. So one thing is that uh, data is the most important part of any machine learning model training or data analytics. And collection of domain-specific data is actually very hard because we have a lot of data available to us in the internet, but one of the main challenges of this is how do you actually mine for the data you're looking for? If you're just looking for cybersecurity data, it becomes extremely difficult. You may have some domains that you want to scrape the data from, um, CrowdStrike blocks, your CVE advisories, but um, well, how many domains can you actually look at? You can look at 100 domains, maybe 500 domains, but uh, in the grand scheme of things, the data isn't enough because LLMs require actually a lot of data to train. The Llama 3.1 models, which are the leading open source models, were trained on 15 trillion tokens. If you convert that into the words for English, on average, one word is equals to 1.3 tokens. So they were trained on roughly 10 trillion words, which is larger than any single library at any university. So here comes Common Crawl. Well, Common Crawl is a non-profit organization that crawls the webs. The web creates the snapshots of web pages, and they've actually made the snapshots available to anyone. It is like Internet Archive or any Wayback Machine that you use, but instead of using the UI, you can actually access it using programming languages or whatever APIs. It's hosted on AWS, and there's a link for the organization. Some of the core maintainers and contributors for Common Crawl are actually the contributors for Internet Archive and Wayback Machine. And these save in WARC or WET formats. I think I mentioned that. I forgot. So yeah, why use Common Crawl? It's the web, and it's free, and it contains almost all of human knowledge accessible, whatever is available on the internet anyways. But there are two fundamental problems. How do we know the web pages to download for content? How do we actually decide that the web page is important for us? And what if we just need the web pages related to cybersecurity? How do you actually mine the data? Okay. So this is where the actual research starts for me. Common Crawl provides a web graph of crawl links. So a web graph of crawl links means that there is a web graph where the domains are the nodes, and there is an edge if there is a hyperlink between the web pages. And the web graph is actually massive because they have more than 100 million nodes and 1.8 billion edges for every web graph they release. So it's a lot. It's a very big graph. As I said, the nodes are domains and edges between domains are present if there is at least one hyperlink between them. Do you guys know about what a hyperlink is, or do I need to explain to anyone? Yeah, hyperlink is just a link that contains a link to another web page. If there's a hyperlink between them, then there's an edge. So what do I do for my applied research? I rank the nodes using eigenvector centrality. I separated nodes into different communities using modularity maximization algorithm and searching for the optimal cybersecurity community. I used some custom heuristics using known good members of community and size of community and modularity. We'll look at what those words mean in a bit. So just what I used for the project, Python, a lot. Scikit network, it is for working with graphs, calculating the centrality scores, the eigenvector centrality scores, largest connected components, community detection, joblib for creating the memory mapped files, because the web graph just contains the data in an adjacency list. So if you have to compute a matrix, it's going to be a huge matrix, because now we're talking about 100 million into 100 million size matrix, which if you don't use sparse matrices, then it amounts to almost a petabyte of data. And obviously we cannot construct that. and GPUs, because we have to do a lot of matrix multiplications and linear algebra stuff. So handling those operations with GPUs speeds them up by a lot. So node filtering, why do we need to do node filtering? Because 100 million nodes, again, 100 mil into 100 mil, that's going to be a large number. We cannot deal with all of that. I couldn't deal with all of that using my desktop. So graph primer, just because I said degree, degree is the number of connections and edges for, or the number of edges for a node. So let's say if a node is connected to 3 other nodes and it has a degree of 3. Doesn't matter if it's an incoming connection or an outgoing connection. The degree distribution of nodes in real-world networks are right skewed. That means that there are nodes that have lower degrees. There are more nodes that have lower degrees than there are nodes that have higher degrees, which means that there are certain, well, let's just look at it as web pages, right? So there are web pages that have a low number of hyperlinks connecting them than pages that have a high number of hyperlinks connecting them. Google.com might have a large number of hyperlinks because it's very well known. But if you just look at some security blog of some random person, they might not have it as much, or just any definition. Yeah, so one of the things I did was removing nodes with a degree less than 2, which means that they only have 2 connections, 1 incoming or 1 outgoing. This means that only 1 other node has referenced them, which means that the node itself isn't that popular or important. Yes, I think that covers it. This is taken from one of the networks, which is what I was talking about. If you look at the x-axis, this is the number of degrees or the degree for each node. You can notice that the distribution is right skewed, and there's actually a lot of nodes that have low degrees, and there are nodes that have high degrees. And this is true for this network, the command crawl web graph, and any real-world network. This is how the graph looks like. So yeah, so first thing, remove nodes with low degrees. Second part of the node filtering. Now I deal with centrality measures. Centrality is the importance of node for definition. And it's actually ill-defined because many people or different people may have different definitions of importance. Some of the ways that people define importance is the one with the most connections, which is the degree centrality, or the one with the most important connections, which means that, so if there's a search engine connecting multiple web pages, then they might have higher centrality because, well, they're connecting multiple web pages and people go on to the domain a lot or use the web page a lot, which is the first point. The other point is important because that node serves as a bridge between subnetworks or communities. So there might be news websites that report on cybersecurity, but there might also be news sites. The same news site might also report on business part of things, which means that they are effectively connecting different communities, which makes them sort of important. So yeah, importance is actually how you define and then convert it to mathematics and everything. Looking at some popular centrality measures, there's degree centrality, which we have talked about. Eigenvector centrality, this is what I used. Eigenvector is, so if there is an important node and that important node is referencing another node, then what it does is it shares some of its centrality score to the other node, which means that if there is a high number of incoming connections and those incoming connections or connections are higher in importance, then that node will have higher importance too. Closeness centrality, mean distance hops between one nodes to all others, and betweenness centrality, nodes are there in central locations, which means that if you're to take an analogy, which would be Panama Canal, because it serves as a bridge between different seas, and a lot of the paths contain the canal. So eigenvector centrality is defined with this expression mathematically. If you have not taken graph class, this might be a little bit difficult to understand. But what it is so there's some constant So first of all, what we do is for every connection for a given node I calculate the amount of importance from each connection, and um, then just regularize with a constant. Um, yeah, so that's what eigenvector centrality is. You sum the number of connections and their importances, and then just regularize with a parameter. So what do I do with eigenvector centrality? I computed the eigenvector centrality score for all of the nodes, and then took only the top 1 million nodes after sorting it with highest first. Again, why? Computational resources limitations, because again, if we're just taking 10 million, it's 10 million into 10 million, which is a lot of nodes and a lot of edges. Community detection next. So after we have all those nodes with high centrality scores, we still don't know if those nodes are from cybersecurity community. So what we do is we do some community detection to divide the network and the nodes into different communities, and then try to find the security community within those detected communities. The hypothesis for this was that we can find the cybersecurity communities that can be used for data collection, and it will actually help us narrow down the interesting nodes, uh, which which are the cybersecurity focused nodes. Again, why computational resources? If you just take into account how many web pages there are in a single domain, that number multiplied by the number of nodes is the number of web pages we have to process to mine for the data, which becomes too much. So again, community detection are not very well defined too. There are ways that communities can be defined. So one of the ways that people do community detection is maximize the number of interconnections within a subnetwork, which means that if there are nodes that continuously or regularly talk with each other, or even if there are a group of people that regularly talk to each other, we can use that as a feature that say that that group of people are actually a subnetwork or a community. Um, yes, so modularity is a metric that helps to quantify the density of connections for a given configuration of community assignment. It can be defined as the fraction of the difference between the expected and actual edges in a group of nodes when it is divided into communities. Why do we do that is because we compare it with a random network. So if a node has more edges than it's supposed to have if randomly distributed, then we can say that the nodes are of the same type of belong to the same community. And it so shows signs of assortative mixing, which is that people or nodes that are like each other will be connected to each other more. This is the formula for modularity. It looks scary, but the AIJ is just the adjacency matrix, which is the actual number of edges for a given pair of nodes, and KI/KJ by 2M is the expected number of edges that should exist given a random network. The Kronecker delta GI/GJ means that they are in the same group. So what it essentially does is, if we have a configuration that divides different nodes into different communities, how many of the edges are preserved and how many are expected? So if there is a large number of edges present within that configuration than expected, then it means that it has a good, or the configuration is actually good. So the objective for the community detection for using modularity is we try to maximize the modularity, which means that we try to maximize the density of connections within subnetworks. And we use a simple algorithm for doing that, which is the node moving algorithm. So this is actually a recursive algorithm. For the first step, what we do is we assign each node to different groups or communities, uh, which might be the number of nodes that are present. So what we do is we assign each node to their own groups, and then randomly pick a node and change the community to one of the other nodes. And we compute modularity for the configuration. If modularity increases, which means that the number of edges are preserved. Then we keep the configuration, or if it decreases, then we backtrack and go to another configuration and repeat and rinse. One of the problems with this algorithm is that the initial assignment of nodes affect how the communities are made, which is why people don't usually use this, but I used it because it was the simplest of all, and computational resources. So the last part for detecting the security community is choosing which community that you're interested in. So for this, what I did was I initially collected a number of domains that I was interested in, um, which were CrowdStrike, sort of that post a lot of dark reading, those domains. So what I did was I checked those, I collected 10 or 15 domains and checked whether those domains were in the communities that were detected using modularity maximization algorithms, and sort of take the percentage of those nodes present in each community, rank them by the percentages. Another thing is choosing based on the size of the community, because there's a parameter R for the modularity maximization algorithm that controls how big the communities are, which means that if I want a really fine-grained community, I can choose um, a higher R, which means that I will get smaller communities or a smaller amount of nodes, but they would be highly connected to each other. Choose based on finite modularity of the network. This should be given by the modularity maximization algorithm. Next steps, well, that was all I did for the research part of it. These are just working with the data that were extracted from each of the nodes in the community. Using the domains from the security community detected, parse the wet WARC records, which means that converting them into text only, because WARC files are essentially web page archives. And you also have to download a lot of data, manage all of that. At the end of this whole thing, I had about 2.8 million websites that I had to parse and make usable. Clean data, of course, parse the HTML, clean text, deduplication, language filtering, child safety content, remove profanity, filter data according to relevance quality, which I don't think I'll cover today. Again, next steps, use the clean data for pre-training LLMs, but still you have to clean them, make sure that the stuff like the tab characters are removed, the new line characters are removed, Unicode is parsed. Then use the data to generate instruction data sets, which is just prompt and answers to those prompts. Use SFT supervised fine-tuning for fine-tuning the LLM or RL-based methods, and use the data to create a ranking model for data ranking. Because once you have collected all of the web pages, now what you can do is you can train the reward model and then continually scrape for new links, rank that new link, and if the data is considered to be high quality, add it to the training data set. I was thinking of doing a data set demo, but I don't know if I can do it on this laptop. I just wanted to show the data set that I was able to create. Just need a browser.
You just need a browser? Oh,
Yeah. Okay. So these are the scored. Wait. All right. Cool. So these are the texts that I extracted using the process. As you can see, there's the URL which I extracted from each of the domains from the cybersecurity community, and then the text from those. Wait, I have to scroll this. And the text from all of those web pages. I use the Llama model, the 70 billion parameter model, to rank or give scores to the extracted content. As suspected, most of the web pages do not actually contain good data to train the LLM, but due to the size of the data that was collected, even the top 1% of the maximum scoring content is 30K web pages, which is actually a lot, and doing it with humans isn't possible. After the scoring part, what I also did was make the instruction data set, which is actually just creating the prompts from the data itself. Wait, I have to go back. Let's just look at some of the answers and instructions. Wait, okay, cool. Let's just look at this. All right, cool. Let's see, do certified. Okay, cool. I don't really want it to be. So these are some of the web page content that I extracted using the method. Let's just read through one. The most advanced cyber attackers try to look like the administrators abusing. Looks like good content. If I can scroll, I could probably show the instructions that we can extract, but it's kind of hard. The text is still gone. Holy crap. Well, I don't think that's possible. But using the text or whatever content that was extracted from the website, now we could create instructions. Also, you could also create a bunch of things. We submitted a paper to ASAC Europe that was accepted, where we used a lot of CVs to create questions, CWEs to create those questions, MCQ questions, or just open text questions, and then evaluated with humans and AI and compared. Well, in our paper or the research that we did, humans actually lost to GPT-4 and some of the AI models. And the questions, some of the questions were like, okay, based on this scenario, which of the things that you think is correct? Select one. All right. Select one option from the 4 options, stuff like that, which is quite kind of interesting. For me, the research hasn't stopped here because I still have to create more instructions, train more LLMs, and try to release the paper. By the way, this is still ongoing. I don't know if I should say this, but disclaimer, please do not copy this or work on this without contacting me first. Thank you.
You have earned a RITSEC lanyard for your first presentation. Congrats.
Cool. By the way, any questions? Anyone? All right.
Is there a way to intentionally sabotage something like this?
Yes. Very good question. This is AI red teaming, right? So one of the